Hey, it's Alex from EDD Academy, and today I'm going to be looking at the derivatives of exponential and logarithmic functions. So just like we did with the sine and cosine functions in my last video, I want to see if we can determine the derivative of the exponential function just by looking at its graph. And let me change colors here. Okay, so when we think about the definition of a graphical derivative, we're trying to find the slope of the tangent line to various points on the graph. So we can look at various x values and look at the slope at those points and see if we recognize a pattern. So let's take x equals 0. So right here, the tangent line to e to the x here, it looks like it matches e to the x. It looks like it's almost on the line e to the x. Okay, so that's interesting. Let's look at x equals 1, which is right here. Once again, the tangent line seems to follow the actual graph. So that's weird. Let's try it one more time. At x equals 2, it does the exact same thing. The slope of the tangent line, or rather the tangent line at every single one of the points we've looked at, is the original graph itself. So what does this mean? This means that the derivative, d dx, of e to the x, well, like we saw on our graph, it's just e to the x. It appears to be the same function at every single point. That's really, really interesting. And if you're not quite sure, which I'm sure some of you may be, let's look at some negative x values. Okay, let's take x equals -1, for example. Yep, still follows the same pattern. X equals -2, exact same thing. And then we have an asymptote here, so it wouldn't be fair to draw the tangent line, but at every single point on the graph of e to the x, the tangent line is e to the x. That's super cool in my opinion, and you'll see as you continue your study of calculus that it's actually very, very unique. So now that we've determined the derivative of e to the x, graphically, we want to put it to test with some examples, right? So I've listed out 2 examples for e to the x, but before I go into them, I want to note that if you have experience with calculus before, you might have seen a different way to find the derivative of e to the x, and it actually uses a technique called implicit differentiation, which is a tool that we haven't quite added to our repertoire yet, and we'll actually see that proof in chapter 3, which is composite, inverse, and just other general derivatives. So I just wanted to put that out there. Okay, now we can go about our example. So we want to find the derivative, or let's change colors. We want to find the derivative, d dx, of 6 sine x minus 4e to the x. So this is a subtraction rule. The subtraction rule we learned a couple videos ago. So we can split up this derivative into the derivative of 6 sine x minus the derivative of 4e to the x. And what is the derivative of 6 sine x, you say? If you remember our last video, the derivative of sine of x was cosine x. So that just means that the derivative of 6 sine x is, well, 6 cosine x. Remember, we can take out this 6 in front of the d dx because it's a constant, so we have 6 times the derivative of sine of x, and that's 6 times cosine x. And then minus the derivative of 4e to the x. So we learned that d dx of e to the x, just regular e to the x, is e to the x, right? the same thing applies. We can pull this 4 out here to the front, so we have minus 4 times the derivative of e to the x. And the derivative of e to the x is just e to the x. So we have 6 cosine x minus 4 e to the x. Our derivative is as simple as that. You'll see many of these examples involving exponential and logarithmic functions. Because their derivatives are rather simple, these more complex derivatives involving multiple terms are also going to be rather simple. So let's take a look at example 2. Example 2 reads, find f prime of x of f of x when f of x equals 3e to the x plus 10x to the fourth. So we want to find the derivative of 3e to the x plus 10x to the fourth. Once again, we see that we can use the derivative addition rule on this. So we have that the derivative of 3e to the x plus the derivative of 10x to the fourth, because we just split it up real quick. So the derivative of 3e to the x is just 3e to the x. It's the exact same thing, no matter what. So 3e to the x. And the derivative of 10x to the fourth, what is that? If you've been following our EDD Academy playlist, you'll note that this is actually a case of the power rule. And I won't go over the power rule because you should be pretty well familiar with it by the time you get to this video. But so the derivative using the power rule of 10x to the fourth is 40x cubed. And that's our derivative. Now we're going to be doing the exact same thing with the logarithmic function, which I have also graphed here. I took this from Desmos. So like we did with the exponential function, I want to analyze the logarithmic function, the graph here, at different x values. So we'll start, let's say, at x equals 2. The graph at x equals 2 seems to be, the tangent line at x equals 2 seems to be, well, a line with slope 1/2. It looks to be the line y equals 1/2 x. Okay, what about, let's say, x equals 4? So right here. The curve flattens out, so the tangent line flattens out, and it looks actually to have a slope of 1/4. Okay. I think I'm starting to see a pattern. What about 1/6 and 1/8? Oh. Once again, it flattens out more and more and more. So the higher the x value, the flatter and closer to 0 the slope of the tangent line is. What does that mean in terms of the derivative? Well, it means that the derivative is inversely proportional to the x value we're looking at. So we can write d dx of ln of x is, so I said inversely proportional, so that means 1 over the x value. And if we consider this statement here, that the derivative of ln x equals 1 over x, it actually fits our graph. So I'll go outright and say it. This is actually our derivative. We won't be proving it in this video, but yeah, just looking at our graph, the derivative of ln x is 1 over x. Looking at some examples now on the next slide, we want to find the derivative f prime of x of f of x when f of x equals 5 cosine x minus 2 ln of x minus 14x minus 1. Okay, so we can go about this by rewriting first. So d dx of this function f of x here. I think we've gotten pretty familiar with the subtraction rule, so I'm going to go ahead and not rewrite this individually, like d dx of 5 cosine x minus d dx of 2 ln x, like etc., and just, so let's consider, what is the derivative of cosine x? We learned last video is negative, that the derivative of cosine x is negative sine x. So what does that mean in terms of this derivative? It's, well, negative 5 sine x. Okay, so moving on to the next term. We just learned that the derivative of ln x is 1 over x. So what does this mean when it's multiplied by 2? Well, it's just minus 2 over x. Instead of 1 over x, you're multiplying it by 2, so it's 2 over x. And the derivative of 14x is just 14, so minus 14. And the derivative of 1 is a constant. Our constant rule says that the derivative of a constant is just 0. So that's our derivative. On to the final example. A very similar problem in regards to what it's asking, but we have a different function. So, find f prime of x of f of x if f of x equals negative 8 sine x minus 9 ln x. So, rewriting this, we do the same process as before. So, we have the derivative of sine x is what? Cosine x, right? And we just multiply that by negative 8. It's as simple as that. So we have negative 8 cosine x as this first term. And what about this 9 ln x term? Well, this is just like the 2 ln x term from the previous slide. We just take the derivative of ln x and multiply by 9. So we have 9 times the derivative of ln x, which is just 1 over x. So if we rewrite this, we have the first term stays the same, nothing happens to it, negative 8 cosine x minus, well, 9 over x. And that's our derivative. Yeah, it's as simple as that. Until we actually learn the chain rule in chapter 3, the derivatives of exponential and logarithmic functions are just going to be as simple as this. So, yeah, thanks for watching.